In the last video, we talked about the syntax and the proof theory for modal propositional logic, and we ended with a list of sample problems which you can work on for extra credit if you'd like. In this video, we talk about the semantics for the system. As I told you, the semantics for modal propositional and quantified modal logic were developed in the early 60s by Saul Kripke when he was 16 years old. Kripke is the most famous person in the history and philosophy of modal logic. In any case, the semantics that we will look at is the semantics derived from Kripke's work. You know what a model is in propositional logic. Here, in order to understand how to extend that, we're going to add a couple of things to the sort of thing that we had in truth tables and propositional logic in standard first-order logic. So there's going to be something similar to what truth tables did in standard first-order logic in our models here. But in addition to that, we're going to add two other elements. W we'll get to first, but R is going to be the relation that I talked about when we were talking about characterizing different kinds of necessity. So W is a non-empty set of objects. Think of them as possible worlds. Kripke called them indices, the plural of index. It doesn't matter what they are. They can be anything whatsoever, but intuitively, we're going to think of W as a set of worlds. R is a binary relation on W. So if you've got two worlds, W sub 1 and W sub 2, R can hold between them or not hold between them. R can be any binary relation at all on worlds. I is a two-place function that assigns false or true, 0 or 1 to each sentence letter relative to each world. So it's just like truth tables, except that now we accommodate the place for the world. For each sentence letter alpha and each world in our set of worlds, the interpretation of alpha at a world is either 0 or 1. So that's how we understand the interpretation of alpha at a world is either false or true. Here, the elements of the ordered triple are, again, a possible world, an accessibility relation on worlds, and an interpretation function. I characterize R as an accessibility relation just because we're going to use the language of accessing or sometimes seeing to explain when one world can be gotten to from another world. These are metaphorical concepts. You can't travel from one world to another or anything like that. But when a world is possible relative to another world, then it is accessible from that world. And so if W2 is possible relative to W1, then the binary relation holds between W1 and W2. The first two of these, the worlds and the relation, are sometimes called the frame for the semantics. So we could say that a model is an ordered pair consisting of a frame and an interpretation function. Notice that there are ontological commitments built into this story. We are, for example, it looks like, committed to a set of possible worlds. Reality is a logical space consisting of the actual world plus a whole bunch of possible worlds. You might not like that. Philosophically, you may think that's way more than there really is to reality. If you want to be non-committal about there being such worlds, you have to do something to try to construct them from other things if you're going to use this semantics. So one way to approach this is just to say, David Lewis does it this way. There really are alternative possible worlds. They're as real as the actual world. End of story, no problem. But suppose you're a bit squeamish about positing that many new things, that many possibilities. Then you have to construct them out of something else. There are lots of attempts in the history of philosophy of the 20th century since C.I. Lewis and Kripke started working that try to do so. The two most famous are Carnap did it in terms of syntax and what he called state descriptions. So he took all the set of atomic formulas for a language, and a state description is on-off switches for the entirety of the set of atomic propositions. So you do on-off switches, true-false switches for each atomic formula, and a state description is the big conjunction of on-off switches for each of the sentences, each of the atomic sentences that are in there. You might think, well, that's all we mean by a possible world, a big state description. That's a syntactic effort. You can also do it semantically. You might say, well, a world is just a maximally consistent set of propositions. It turns out that raises problems because maybe there isn't a consistent notion of completion for a maximal consistent set of propositions. Think about set theoretic paradoxes. The set of all sets that are not members of themselves turns out to be an incoherent notion. And some people think the same thing will happen with the notion of a maximal consistent set of propositions. So instead, some people say, I'm not going to talk about sets of propositions. I'm just going to talk about a big conjunction. A maximal consistent conjunction is a proposition that contains every other proposition, either it or its negation, as a conjunct. These are interesting attempts to try to construct the notion of a possible world from other things that you're already committed to the existence of. We don't need to investigate whether or not these are successful accounts, because that would be relevant more to the philosophy of logic and general metaphysics than a logic course. I just want to flag that these are ontological issues that many people balk at, and they worry that if we're going to do modal logic, we're going to have a bloated ontology, and nobody wants a bloated ontology. Well, actually, some people do, but you shouldn't. That's the idea. So, can you build them out of other things? Maybe you can in one of these two ways. Maybe there are other possibilities, but that's an interesting philosophical project to look at some other time. Once we have this apparatus in place, the notion of a model for modal propositional logic, the important thing is to get to a valuation function. We need a big V, and that's familiar as well from our CIDR semantics for first-order classical logic. So a valuation function is something that generates a number. 0 or 1. Intuitively, 0 is false, 1 is true. So a valuation function for a model is a function that assigns 0 or 1 to every well-formed formula in the language, where alpha is an atomic formula and W is a world. Here's what we get. The valuation on the model for an atomic formula and a world is just the interpretation of the atomic formula for that world. And remember, the interpretation for an atomic formula at a world is itself a 0 or 1. So clause 1 is about atomic formulas, and it generates a number, 0 or 1, for each atomic formula. Once we have numbers for the atomic formulas, then we just introduce the usual clauses for all of the connectives in the same way we did in standard first-order logic. So negation switches the 1s to 0s and 0s to 1s. The clause for arrow tells us that the arrow formula comes out true at a world if and only if either the antecedent is false or the consequent is true. The value for a boxed formula is new, but for each of the other connectives from standard first-order logic, you can see how the valuation function is going to be built once you understand how negation and arrow work. You can understand how to derive all of the others from those too. What about for the box? Well, it says, consider all of the worlds, all of the possible worlds that are accessible relative to W, the world where we're trying to assign a value to the boxed formula. So take all of the worlds that are accessible, then the valuation at each of those accessible worlds is itself 1. That's why it's called an accessibility relation. The box is like a universal quantifier over worlds, but the only worlds that are relevant are the worlds that are accessible from the world that we're trying to assign a valuation to the formula in question. So you could have said, if we just went with an absolute unrestricted notion of necessity, a box formula is true at a world when it's true at every world. Similarly, a diamond formula would be true at a world if it's true at some world. That intuitive notion has to be replaced to include a reference to the accessibility relation, because there are notions of necessity that make some worlds accessible and leave some worlds as inaccessible. So what we do is we restrict. So we start out with, let's take all of the worlds that are accessible. A boxed formula is true at a world if it's true at each of the accessible worlds. Once you get that far, it's easy to see how to define clauses for ampersand, double arrow, diamond, and fishhook, given the definitions of these in terms of the connectives above. So let's just take diamond because it's the most obvious addition to the machinery we had in the semantics for classical first-order logic. A diamond will then say something similar. A diamond formula will come out true at a world, just like a boxed formula comes out true at a world relative to some class of accessible worlds. The boxed formula comes out true when the formula in question is true at every accessible world. The diamond will come out true if it's true at some accessible, at least one accessible world. A couple of thoughts about the accessibility relation. It says intuitively that this relation obtains between W and V just in case V is possible relative to W. We've talked about this before, but you might think that every world is possible relative to every other world, but that ignores the fact that there are more and less restrictive notions of necessity. And because there are more and less restrictive notions of necessity, the more restrictive worlds, the more restrictive notions of necessity will appeal to a smaller collection of worlds, a smaller set of worlds than the less restrictive notions of necessity. So think about this one. I can't run a mile in under 6 minutes. Nothing can accelerate beyond the speed of light. There's a difference between those two notions of necessity. The first one is a much more restrictive notion of impossibility than the second. Perhaps there was a time in my life when I could run a mile in under 6 minutes. Those days are gone. But that's a more restrictive notion of necessity than something about the laws of nature relative to the speed of light. Einstein said nothing can do what's posited when you talk about accelerating beyond the speed of light. So for each kind of necessity, we want axioms to govern the operator, and we want to characterize the accessibility relation to match the axioms chosen. If we don't get an appropriate match, we won't be able to prove soundness and completeness. So here are how the axioms are related to restrictions on the accessibility relation. For system D, which we haven't talked about to this point, we get box phi implies diamond phi. For that logic, the important relation is one which is serial. What is it for a relation to be serial? You can look this up. You can look up the meanings of each of these names in the Cider book. I will leave serial for you to look up. You can probably figure out what it means. Though, what it ought to mean is there's always some world that's accessible from any given world. The first logic that we start working with seriously, though, is system M, or as I call it, T. The distinctive axiom for it is box phi arrow phi. And the relevant relation restriction for this axiom is the reflexive relation. The reflexive relation is if you've got a world W, W is always accessible from itself. So the relation says this. For any world W, W is always accessible from W. That's reflexivity. One way to think about the reflexivity requirement is in terms of the alternative version of the T axiom. If you recall, I told you that an alternative formulation of it tells you that you could also express that axiom as phi implies diamond phi. Go back to the other video if you have forgotten why that's true. Reflexivity says W is always accessible from itself. So one way to get a guarantee that phi arrow diamond phi will hold, you might only have in your model one world, W. That means phi arrow diamond phi can't hold unless W is accessible from itself. Remember, to say diamond phi tells you that there is some accessible world in which phi holds. So if W is accessible from itself, then if we've got phi in a world, we can also put diamond phi in that world, since W is accessible from itself. For S4, we get transitivity. Now, transitivity is this. If A is related to B and B is related to C, then A is related to C. That's transitivity. That's the distinctive relation for S4. The distinctive relation for B is symmetry. Symmetry is if A is related to B, then B is related to A. And finally, S5 is an equivalence relation, which is reflexivity, symmetry, and transitivity all put together. So S5 is the most general kind of modal logic because it incorporates everything from T and S4 and B, T or M, whichever way you want to think about it. So when we're doing semantic work, we have to make sure if we're doing semantic work in S4, you can't appeal to symmetry or equivalence. You can only appeal to transitivity on the worlds. If we're doing work in the semantics, constructing models in the semantics for system M, all you can use is reflexivity. It's important to know which system you're in and which relation holds on the worlds for the system in question, given the axiom. The important thing that we want to be able to do is use this semantic information to show which argument forms, which claims about semantic consequence hold and which don't. And the way we do that is by trying to construct countermodels. Because remember, if a proposed semantic consequence relation holds between, say, A and B, the way in which you demonstrate that that's false is by constructing a countermodel, a model on which the premises are true and the conclusion isn't true. When we're constructing models and countermodels, there's an important role that arbitrariness plays in the construction of a model that I need to flag for you because it can corrupt your attempt to construct countermodels. Go back to propositional logic for a moment. Here's a really nasty problem to put on an exam. It has all sorts of interesting claims in the premises, and then we're told that this formula follows from everything that comes before. When you're trying to construct a countermodel to this problem, you're looking for a case where the conclusion is false and each of the premises are true. You were probably taught this as the short form for constructing a countermodel rather than having to construct the entire big long truth table for this problem and then looking for lines where all of the premises are true and the conclusion is false. If you construct the big long truth table for this problem, you're going to have, how many atomic formulas? 1, 2, 3, 4, 5, looks like 5. So you'd have a truth table that had 2 to the 5th number of lines, which is, I think, 32. That's a lot of work. So the simpler way to approach things is just assume that all of the premises are true and the conclusion is false, and then trace the implications of that assumption. Now, when you do that, you get stuck on this problem immediately. You can, in the third premise, learn that T is true and the conditional that's the second conjunct is also true. So you know that T is true over here and T is true here. And then at that point, you just ran out of implications for your original assumption. When you're doing short forms for truth tables, the next thing you do is you make an arbitrary assumption and see if the problem works out that way. Typically, that means, in this case, for this kind of a problem, you'd go to the conclusion, pick one of these two to be false. Suppose it's R. To keep track of your work, I always require that when you make an arbitrary assumption, you mark it as arbitrary. because what you're trying to do is make a consistent set of assignments where the premises are true and the conclusion false. This arbitrary assumption tells us that we're now looking at exactly half of the long truth table. Since there's 32 lines on the truth table, we're now ignoring 16 of the lines, and we're betting that in the other 16 lines, there is a line with true premises and a false conclusion. That may not work out. There may be no such line in those 16 lines. So does it follow that this argument is valid if you generate a contradiction from this arbitrary assumption? Of course not, because it's arbitrary. You have to look at the other 16 lines. That's why we mark our arbitrary assignments, to keep track of the fact that if things blow up on us, our work isn't done. We have to go back and switch our arbitrary assignments. So when you have an arbitrary assignment, you have to indicate it in some way. For predicate logic, you have a similar kind of arbitrary assumption when you construct countermodels. So suppose you have this claim, that nothing is C follows from those pieces of information. Well, you have a choice about how many things to put in the domain. That's an arbitrary assumption. So you start out, you have to have at least one. So you start with the assumption that there's one thing in the domain and see if you can give an account to the extension function for the predicate letters A, B, and C, and D so that the premises are true and the conclusion false. There's no guarantee that for a model that has only one thing in the domain, you'll be able to do that. Suppose you can't do it. Nothing follows about the validity or invalidity of the argument from the fact that you can't do a countermodel with just one thing in the domain. You then try with two things in the domain, and so on. Maybe that won't work either. In fact, there are sequent examples where only an infinite domain will show that the argument form is invalid. So if we start with an assumption of domain size and can't generate a countermodel, nothing follows. Something similar happens in modal propositional logic. We need to note when arbitrariness is present in our model, and we need to keep track of that, because when we make arbitrary assumptions and then things blow up on us, it doesn't show that a countermodel isn't possible. It just shows it's not possible given that arbitrary assumption. So you have to go back and switch, get rid of it. In the Sider textbook, the symbol he uses is a dagger symbol for when an assumption is arbitrary. In addition, Sider uses asterisks, both above and below formulas, to show respectively formulas that require something at every world and at some world, respectively. So an asterisk above, this is a formula that's going to have to appear in every world. Asterisk below, it's got to be somewhere. For the most part, I'm not going to use the asterisks. Those are easy enough to keep track of. If you have a boxed formula, it's going to have to be true at every accessible world. So you just have to check. And a diamond formula has to be true at some accessible world. You just have to make sure that when you have diamond and boxed formulas, that you trace the implications of that for all of the respective worlds before concluding constructing a countermodel. So for a formula for which we want to show that there's a countermodel, we start with a world in which the claim is false and trace its implications for the system in question, either system T, S4, S5, or sometimes, rarely, we'll use system B. For example, we know that the S5 axiom isn't valid in S4, so we should be able to construct a countermodel to it. So our attempt here is to give a counterexample, a countermodel to the S5 axiom in S4. For that, we need to know what the distinctive accessibility relations are for S4, and that is transitivity plus reflexivity, because T is going to be required for any further system such as S4, S5, or B. So we're going to give a counterexample in S4. We begin then by constructing a world in which the distinctive axiom of S5 is false. For that to be the case, the conditional in question has to have a true antecedent and a false consequent. If you don't see that that formula is equivalent to the false consequent, just think of operator exchange. I could have written down the negation of box diamond P and then done operator exchange to get to this. But I'm trying to be efficient. I don't want to add stuff to a world that is pretty intuitive and fairly obvious to see. It just makes the diagrams more complicated. So I skipped some steps. You can do that too. Just make sure you don't make a mistake in identifying equivalent formulas when they really aren't equivalent. So I'm assuming this can be shown to follow from the negation of this, and it's easy to see how. So I now have two possibility claims generated from my original assumption. That means there has to be a world that realizes each of these possibilities. So that's what I do. I first build a world to realize the bottom possibility. If this is true, then there's a world where the outside diamond is dropped and everything else is true. And then I trace the implications of this assumption. By operator exchange, that gives us box tilde P, box neg P, and then the box tells us that every world accessible from this world is a world where neg P is true. Now, since we're working with S4, every world is accessible from itself. That's the reflexivity assumption. So you know this when you start. The first world is accessible from itself, and the second world is accessible from itself. This is the first time where the accessibility relation forces us to do something. It forces us, if we've got box neg P, to put neg P here. So when we started this problem, we knew, I'm going to add these arrows to the diagram in a moment, but we knew when we started that the first world is accessible from itself, and so is the second. Every world's going to be accessible from itself. We also know that the second world has to be accessible from the first, otherwise it can't be the world to realize this possibility. So we know that some arrows are going to be appearing here. We haven't put the arrows in yet, but we know that they're going to be there, and that's why we have to put neg P in the second world. That's enough for the bottom possibility assumption. There's also the top, the first possibility assumption. We need a world to realize the possibility of P. Now here you have a choice. You can't use the second world to realize that possibility because it's already got not P in it. You could use the first world. I chose to build a third world. There's no particular reason why I chose a third world, but I am assuming that there is a third world for my model, and it is a world that realizes the first possibility, diamond P. Then all of the arrows get added, alpha and the names of the worlds. We have alpha, B, and C, or A, B, and C, but I think that's supposed to be an alpha. So alpha is the world we started with, in which the S5 axiom is false. We traced the implications of that assumption, and then we built B and C to realize each of the two possibilities in question. That means C has to be accessible from A, and B has to be accessible from A. So we put in those arrows. And every world has to be accessible from itself. That's the reflexivity relation. We are now done because the only other relation for S4 is transitivity. Transitivity says if one world is related to a first world and a third world is related to the second world, then the third world is related to the first world. In other words, since we only have 3 arrows here, 3 worlds here, if we had both that R relates alpha and beta and R relates beta, B and C, not beta, then if we had both of those, we'd also have to have R relating alpha and C. Is transitivity satisfied here? Yeah, the answer is yes, because this conjunction is false. The falsity of an antecedent guarantees the truth of the arrow formula. The antecedent is false because B and C are unrelated to each other. So this is a model on which reflexivity holds. So it's a counter model in T. It's also a counter model in S4 to the S5 axiom. It's a counterexample to S4 because transitivity holds on this counter model. We can also construct a counter model in B to the S5 axiom. Notice that this model is not a B counter model. Why not? The distinctive relation for B is symmetry, and symmetry fails. For symmetry to hold here, these arrows would have to run both ways. They do not. So it is not a counter model in B, but it is in both T and S4. If we want to do a counter model in B, let's go this way. Let's start out roughly the same, but I'm going to put not P in the first world. I'm also going to put the same things in the second world. Now, why did I put not P in the first world? The reason I put not P in the first world is because if I'm going to use the second world to realize this possibility, the arrow's going to have to run both directions in order to satisfy symmetry. Well, if the arrow runs in both directions, this box formula, when you drop the box, the formula in question has to appear in every accessible world. So not only is this second world, B, accessible from alpha, alpha is also accessible from B. So the unboxed version has to appear in this world as well. And then I do the same thing with the third world. I'm going to realize the possibility of P, the second line in alpha, in the third world, C, and I'm going to run the arrows both directions. The only thing I had to add then to get a B counter model to the S5 axiom, I had to make these arrows run both directions rather than just one direction. And when they ran in both directions, I had to add neg P to alpha, because box neg P is in a world from which alpha is accessible. So when you're constructing counter models, you just draw circles for worlds, you put formulas that are needed in there, you trace implications, you add worlds when you need to, but always understand you're making some arbitrary judgments. Now, I'm not marking anything as arbitrary, and for the most part, you don't have to either. But don't forget when you're doing something that's not required. So, for example, I used a third world to generate the possibility in question up here. I used a third world. In the last counter model, I didn't need a third world. I could have put P in the first world. The decision to use a third world was arbitrary. In this case, it's not, because if I had used alpha to realize the possibility of P, I would have put P in here, but I've already got not P because I used B to realize the possibility of not possibly P. So that would have forced my hand to create another world. Last counter model, I didn't need the third world. This time, I would need a third world. Okay, here's some sample problems for you to work out on your own. Again, as before, you can do all of these and turn them in for extra credit. But as before, it's all or none on the extra credit. So here you will do sample problems. Try, if you can, to construct counter models in T, in S4 and S5. If you can't do a counter model, perhaps you can prove which are which. So some are provable, some are not. The ones that are not provable, you should be able to construct a counter model. So try to figure out which are which. If you can do a counter model in a system, you might be able to do one counter model for all three of the systems, but figure out which are provable in which systems and which you can develop counter models in which systems. And here are 6 problems times 3 systems, so that's 18. If you want extra credit, go ahead and work on that. That's all we need to talk about for the semantics of the system. Counter models are very fun to build. If you're having trouble, let's sit down during office hours or some other time, so let me know and we'll work out the details.